So considering a Carnot heat engine cycle executed in a closed system using 0.025 kilograms of steam as the working fluid, it is known that the maximum absolute temperature in the cycle is twice the minimum absolute temperature, and the net work output is 60 kilojoules. If the steam changes from saturated vapor to saturated liquid during the heat rejection, determine the temperature of the steam during the heat rejection process. So, here we go. Given. We know it's a Carnot heat engine. So we've identified that, and you just go to the equations, okay? But let's continue. We got steam. TH is 2 times TL. And TL is, I don't know, let's make a number. 50. And this would be 100. You're gonna realize later on it doesn't really matter. We could have picked any values. I just picked some easy ones. And the W net out equals 60 kilojoules.
Where'd you get the 50?
I just made it up.
Oh.
So if you would look at the
We're gonna be able to make up a number though. They're usually gonna give it to us.
yeah, I think most of them will give them to you. Yep. But you'll realize when we do the equation, it's just half. So I just kind of said, well, if they didn't give us anything, you can always make up some. It doesn't matter. So if we looked at our schematic from before, it was from 3 to 4. So this is the section we're looking at. So I'm going to do the vapor dome right here. And let's see how much you remember. Let's assume kilopascals, meters cubed per kilogram. Remember this in chapter 3? A long time ago? We're in chapter like, what now? 6? This is a PV diagram. And it said it went from what to what? Yep, saturated vapor to saturated liquid. So that is from what? Here to here, right? Tell me, what do constant pressure lines look like? Like this? Yeah. Yeah. If you did the TV, it would be constant pressure lines, right? They'd go up and over and up. What's that?
Constant temperature lines.
Those are constant temperature lines, the orange ones. Yep. And let's just label these VF, right? And that would be VG3. And we're looking for what? Determine the temperature of the steam during the heat rejection. So we're looking for TL. And we actually have QL going out in that sketch. So heat rejection. Look at that. Nice, beautiful setup. Right? We've identified it's a Carnot heat engine. So we can go, we've identified where we are in the states. We kind of know where we are in the process. And we can start our solution now, right? So Carnot heat engine. And I'm going to put workout equation. So W net out, oops, trying to think
When they
of
say
do we want-
TH and TL, they're just talking about the temperature in one phase to the other.
Yep. Yep. I have just trying to remember if we did. Do I want to just do W net? Yeah, W net. Why didn't I do dots? Because W net was in terms of joules, right? That's what I was checking. So I wrote this down to help you because we're going to look for QL. Because that is what? That's how we need to find TL. Okay? So we need QL. We need this QL to end up finding what the temperature is. Okay? What other equation can we use? Because we need to find QH now, right? But there's some other equation we can use. What's it? We can use the efficiency equation. And I'll show you. We'll get through this. The efficiency is W net, oops, out divided by QH. But it's a Carnot heat engine. We can find it. So therefore, what? QH equals W net, man, I keep doing dots, divided by the efficiency. Okay, so far everyone's okay? All right, so we're going to plug in QH into QL equation. So QL equals W net out over the efficiency minus W net out. So what I defined the efficiency above was for a heat engine. But now that we have a Carnot cycle, which is a reversible system, can you double check? That should be the equation that we had for a Carnot cycle, right? For heat engine? 1 minus TL over TH, right? Okay. So the efficiency of this system is 1 minus, would we say 50 over 100? Which is 1 minus a half, which gives you what? Half. Now, did you notice why we didn't really need to pick these? We could have just kept them TL and 2 times TL and it would have canceled. All right, so now QL equals, that was 60 kilojoules, right? Over 0.5, subtract 60 kilojoules. Guess what you get? 60 kilojoules, right? Because this is 1/2, it's really 2 times 1, yeah. So you get 60 kilojoules. What? That's weird, huh? That just magically happens, okay? So we're almost there, and then the next thing I'm going to show you is kind of something new. So we now know how much Q has been released, okay? And what I'm going to do is I'm going to draw the vapor dome again and label our points. That was supposed to be straight. So we went from the vapor to the liquid. Okay. This is something new that I haven't talked about, but that's fine. If you want to know how much energy was released from that, that's actually what HFG is. Okay. So the enthalpy change between your vapor to that is actually how much heat has been released. Okay. So that's what we define as QL. So how do we find HFG? What are the units on H? Kilojoules per kilogram. So this would be QL over M, right? I don't think there's one like this on the homework. Sorry, but I wanted to show you this so you get an idea of what HFG is. So you get 2,400 kilojoules per kilogram. And once you know that, then what do? Go to the tables and you can interpolate to figure out what you have. Okay, so table A-4.
QL is not really equal to HFG.
Oh, sorry, it's not. Sorry, over M. Yep, thank you.
No.
Yep. You get TL to be 42.5 degrees C.